Okay, so the last lecture ended a bit abruptly, so I'm just going to finish up what I was saying over there. And I had almost finished up what I was saying. I was really saying that there are multiple ways of computing the determinant, right? So if you have a matrix such as this, then one way of computing the matrix is you go across the first column and then multiply every entry with its cofactor and then take into account the sign. The sign can be taken into account either you make a checkerboard like this or you compute -1 I plus j. And the reason this works is we can see that this works is because I is the row and j is the column. So if the sum is even, then it gives you a plus sign. If the sum is odd, then it gives you a negative sign. And we can see that over here, the sum is positive. Sorry, the sum is even, sum is odd, sum is even, and so on, right? Sum is odd, sum is even, so on. And it really depends on you, which row or which column. You can choose the columns the column or the row which has the most zeros. So for example, in this case, you should pick the second column because it will make the computations easier for you. So I did the same calculation twice, but in the second time, I picked the second column because over here I just have to find one sort of clear this out. So notice that only one entry is non-zero, so which means that you get rid of the row that this is in the column that this entry is in. So the row and the column for 2 minus lambda, it has a plus sign, and these entries will make up the matrix for which you'll find the determinant, right? So we did write all of these entries, right? The determinant, if you go along this column, then these are the determinant terms, but the entry for A12 and the entry for A32 disappear because they're just zero. So this is going to be zero and this is going to be zero, right? So that's what I was saying before I had a network issue. Okay, so we know what eigenvalues are. We have some idea of what eigenvalues are, what eigenvectors are, and we now have some way of computing them, right? So the way to compute them is to just, so if, let me just recap how we do this. So we first compute eigenvalues and eigenvectors, right? So to find the eigenvalues, you solve the characteristic equation, which is determinant of A minus lambda I equals 0. And we also talked about how many independent how many eigenvalues you can get, right? You can get, if this equation is going to be an nth order polynomial, right? So if you're working with a 2 by 2 matrix, then it's going to be a quadratic equation. It can be a if it's a 3 by 3 matrix, then it's a cubic equation. And so because we know the solutions of polynomials for a quadratic equation, I know maybe I get real roots or maybe I get imaginary roots, right? So in the case when I get real roots, maybe I get 2 distinct roots or maybe just 1 repeated root. And so this is just how many eigenvalues, how many, and here we can even distinguish between real, right? How many real eigenvalues we get depends on how many solutions, how many real solutions do we have for this nth order polynomial that we get from this equation. And once you have all these, once you have the real eigenvalues, you can find the eigenvectors by solving, or rather finding the null space, finding the null space of A minus lambda I, right? Or in other words, you just solve A minus lambda I, x is equals to 0. So finding x is basically just finding the vectors which are in the null space of A minus lambda I, right? Okay, so that was the last lecture, and now we're going to I think move on to perhaps the most important application of eigenvalues and eigenvectors, which is the diagonalization. Diagonalization, right? And this is similar to, the factorizations that we've done so far. So if you remember, we've done two factorizations already, which was A equals to LU, where this is a lower triangular matrix and U is an upper triangular matrix. And we've also done A equals to QR, where Q was an orthogonal matrix and R was an upper triangular matrix, right? So we do these factorizations because they make computations a lot easier for us, right? They make it more efficient for us to solve linear systems, right? And in the same way, we can now talk about the idea of diagonalization, which is we write A is equals to V D V inverse, right? There's lots of ways of writing it, but some write it as U or X. I think in the book it's written as X lambda X inverse, and that's just fine. The idea is that these are three matrices which this A is being broken down into, and I've given it the name of V because this matrix V contains the eigenvectors as columns, right? And this D matrix diagonal, it's a diagonal matrix, right? It's a diagonal matrix, but it contains eigenvalues on the diagonal, right? So we're gonna do a couple of examples, and this V inverse is just the inverse of V, right? That's fine. We'll see how to do that. But the important thing is that you can do this only when. So let me just state a fact from the start, which is if A has n independent eigenvectors, then A is diagonalizable. And you could perhaps see the reason for it. The reason for this fact lies within this statement VDV inverse. See, we're assuming that V inverse exists. And if V inverse can only exist if V is non-singular. And one of the ways V is non-singular is to say that the columns are independent. So if A is an n by n matrix, then all of these are just, by the way, n by n, n by n, n by n matrices. And V has eigenvectors of A as its columns, right? So if the columns of V are independent, that means the eigenvectors are independent. So V will only have an inverse when the eigenvectors are independent, and there are n of them and they're all independent, right? So that's something that we need when we want to diagonalize a matrix. So let's just look at an example. What do I mean? So I think we've done a couple of examples. We can just take them off. Let's take a simple example from the start. So we'll come to this one because this one has a 0 eigenvalue. We'll come to that. Let's take this one. So 2, 1, 0, 3. And what were the eigenvalues? The eigenvalues were 2 and 3. And the eigenvectors were 1, 0, and 1, 1. So it's a fairly simple matrix, right? So you're probably not going to be immediately able to appreciate the advantages, but we'll get to those. So let's just demonstrate the idea. So this is A, right? And let's say, let's just demonstrate the idea that if I do AV, then I will get V times X, right? Sorry, V times D. So let's first demonstrate this idea. What do I mean by AV equals to VD? Right, so I know the eigenvalues, eigenvectors, right? So this is matrix A, and I'm going to construct the this V matrix by putting the eigenvectors. The first eigenvector was 1, 0. The second eigenvector was 1, 1. So I've put both of those as the columns of the second matrix, right? And now, since I know that these are eigenvectors, something is going to happen, right? So this is just x1 perhaps, or x2. But remember that the main eigenvalue equation tells us that when you multiply matrix A with an eigenvector, then it gives me lambda times the eigenvector. So let's see how that plays out over here. Okay, so this is 2, 1 times 1, 0. What do I get over here? So I get 2 over here, and I get 3 over here, and then I get 0 here, and I get 0, 3 is this 3 here, right? So notice that this is, if this was V1 and this was V2, this is just 2 times V1 and 3 times V2, right? Because these were eigenvectors, that was supposed to happen. This was the eigenvalue, right? And this was the second eigenvalue. Okay, and I can, since I know that these are eigenvectors, I can write them in a different way. I can write this. I can take out the eigenvector, which was 1, 0 and 1, 1, and I can put the rest of the entries over here. I can put the eigenvalues over here. So I put on the diagonals, I'm going to put the eigenvalues. So this is, now I'm constructing D, right? So 2, 0, 0, 3. And notice that it's just the same thing, right? If I do this multiplication again, you can notice that I'll get the same thing. 1 times 2, 1 times 0 gives me 2. This value is correct, right? So I get this value. Then if I do this row times this column, I'll get 3. If I do this row times this column, I'll get a 0. And if I do this row times this column, I'll get a 3. So all of these entries do check out, right? So what I've shown you is that A times V gives us V times T, right? Where V is the matrix of eigenvectors, right? So I can just put that over here so that you can see the whole effect of what's happening, right? And this is fairly simple. This was happening because it's not happening because this was a simple matrix. It's going to happen in any case, right? And I'm going to discuss the general case in a bit. So that's the idea, that AV is equals to BT. Let's talk about the general case now, right? So let's say, let A be an n by n matrix with n independent column, with n independent eigenvectors. So let me just move this to the next page because I don't have enough space to carry out this calculation here. So, okay. So this is the general case. So let's say n independent eigenvectors, and let me name them, right? So this is V1 to Vn. These are the eigenvectors. So if A is matrix, let's say I put A here, and I put the n eigenvectors like this. So first column is V1, second column V2, dot, 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 last column, nth column is Vn. Okay, what happens when I do this? So of course, then with each of these eigenvectors, there will be an eigenvalue associated, right? Lambda 1, lambda 2, and lambda n. So this basically, when I say these are eigenvectors, I mean A times V1 will be lambda 1 times V1. A times V2 will be lambda times V2, right? That's the basic definition of an eigenvector. So when I multiply this matrix with this matrix, this A times V, what I get is that I can think of it as multiplying a matrix with one vector at a time, right? So A times V1 will give me lambda 1 V1. So the result is going to be the following. The result will be lambda 1 V1, that's the first column, lambda 2 V2, second column, and lambda n Vn, that's my last column, right? And now this can be again viewed as just, if I extract all the columns and just put the scalars down, just exactly the way I did in this example where I just took out the eigenvectors and just put the eigenvalues in a diagonal matrix, right? So let me create a bit more space for myself. So the matrix over here is going to be lambda 1 on the first diagonal, lambda 2, and and the last diagonal entry will be lambda n, and the rest is 0, right? This empty space is all zeros. So AV gives me VD. And the reason I wanted n independent eigenvectors was that I can do the following. So if AV is equals to VD, this was true. I haven't used the idea of having n independent vectors yet, even though I've put in all these diagonals, right? Maybe some of them are dependent, but if they are independent, then independence of V1, Vn allows me to take V inverse, right? And so I can multiply by V inverse on both sides, A, V inverse, I right multiply them, VD, V inverse. So this becomes the identity V times V inverse, and we're left with just A equals to VD, V inverse, right? So that's the diagonalization process. Okay, and so what do you need to do for this diagonalization? You just need to find the eigenvectors and eigenvalues. As soon as you have them, then you have those matrices, right? And then you'll need to find V inverse, but we'll talk about how to compute this in an efficient way as well, right? Okay. So how is this factorization helpful? Let's see, how is this helpful? The first thing that we're going to talk about is we're going to talk about powers of A. Okay, and let's suppose if you want to do some, let's say I want to find A squared, right? So A was equals to 2, 1, 0, 3. And if I want to do A squared, then I have to do this matrix multiplication, right? 2, 1, 0, 3 times 2, 1, 0, 3. So let's see how many calculations that I need to do. I'll need to multiply this row with this column. So 2 multiplications and an addition, right? So let's count them, multiplications and additions. So I have 2 multiplications and 1 addition. And then I'll need to do that 4 times, right? So 4 times I'll need to do this, which means I need to do 8 multiplications and additions, right? And so, but if I want to do, let's say, A cubed, then I have one more matrix to deal with, which means I'll do another multiplication, which means it will be twice of that. So the way we find matrix powers efficiently is if we have a diagonalization. So let's say I don't want to do all of this calculation, let's say, and you can see that this is simple because it's a 2 by 2 matrix, but for a 3 by 3, it's going to be even more values, right? So it's going to be 3 multiplications in each row and each column, and then you have, as n increases, they grow larger and larger, and we're talking about large n matrices, right? So if you have A equals to VD V inverse, what is A squared? A squared can be written as A times A, which is VD V inverse times VD V inverse. And you can immediately see what's going on because matrix multiplication is associative, so I can basically write the parentheses wherever I want. And this is a nice thing that happens, right? That V inverse and V multiply to give us the identity, which means this just becomes VD squared V inverse. And this doesn't just happen for A squared. If I do A cubed, then A cubed is simply A squared times A, right? So A squared I've already seen, which is VD squared V inverse, and then A is just VD V inverse, and I again get this multiplication of V inverse and V, which means this is going to be VD cubed V inverse. So any power of A, AK, is going to be V dk V inverse, right? And that's a nice little thing to have. And the reason this is particularly nice, now you will ask me, or you should ask, why is this helpful? Because AK has now just become D to the K, and I still have to find powers of this matrix. But remind yourself that D is a diagonal matrix, right? So if I have if I have a diagonal matrix, let's suppose 2, 3, 0, 0, and if I want to square this, then it's just the same as just squaring these entries, right? For a diagonal matrix, you can just individually square the diagonal entries, which means I claim that the result is going to be 4, 0, 0, 9, and you can check that out. The way this will happen is 2 to 4, and then this is just 0, this row times this column is 0, this row times this column is 0, and this row times this column is 9, right? So you get 4, 0, 0, 9, which means if I have a diagonal matrix, right? So if you have D is equals to lambda 1, lambda 2, dot, 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 lambda n, all of these entries with the rest as zeros, then d to the k has to be equals to lambda 1 to the kth power, lambda 2 to the kth power, and then lambda n to the kth power. So all of those multiplications, right? So if you had to do, like, let's say you had a 3 by, or let's say a 5 by 5 matrix A, and then you had to find A to the power 10, which means you have to multiply 10 5 by 5 matrices together, right? Instead, if you can find A is equals to V D V inverse, then A to the 10th power can be found as V D to the 10th power V inverse. And over here, you just have to do what? You have to find the 10th power of what? 5 values. So 10th power of 5 real numbers, right? And then what? And what about these 3? Well, then you have to just do 3 5 by 5 matrix multiplications if you want to do that. You could leave it in this form, or you can just multiply them all together and take that as A to the 10 if you really want the whole matrix to be constructed, right? So this is simplified from 10 5 by 5 matrix multiplications. You just need to do 3, right? Even if you had to do 20, then you just, this number will change, but this number remains constant, right? So that's an efficient way of computing the powers of matrices if you have this diagonalization, right? Okay. Gonna take a little 5-minute break before continuing. Okay, let's continue. So let's do a couple of examples for the diagonalization process, right? We can do this example where we had a zero eigenvalue, right? So 1, 3, 2, 6. The eigenvalues were 0 and 7, and the eigenvectors were minus 3, 1, and what else? So these were the eigenvalues and eigenvectors. So the matrix was 1, 2, 3, 6, and let's just take these with us. Okay, so right, here are the eigenvalues, the example, right? So the matrix was A is equals to 1, 2, 3, 6, right? And this can be diagonalized, right? So we have that A times, so 1, 3, 2, 6 times, let's put in the eigenvectors, minus 3, 1, 1, 2. So this is A times V, and we know that this will give us V times T, which is, let's just put it immediately together because we know what V is, we know what D is. D is going to be 0, which is associated with this, and 7, right? Okay, so this is the diagonalization for a matrix which was singular, right? This was a singular matrix. So see, singularity and diagonalization don't really have anything to do with each other. In that they do, in the sense that if you get a singular matrix, you will get an entry in the diagonal matrix which will be 0. But other than that, it won't affect the matrix from being diagonalizable, right? So you can even then you can have two independent eigenvectors and you can diagonalize the matrix, right? One key part which is missing is to find now I have written this as AV equals to VD. Now we do have to find, we need to write VD, V inverse, right? So we do need this inverse matrix, right? So in the 2 by 2 case, it's easy, or you could do the A identity, the Gauss-Jordan method, where you find the identity by augmenting the matrix with the identity matrix and then producing the inverse where the identity matrix was, right? So that's I think the most efficient way that we have to find A inverse, right? Okay, so we can do that for V, and V is a simple matrix. It's 2 by 2, minus 3, 1, 1, 2. We can do this. So this is just, let's just use the formula, which is 1 over determinant, which is minus 6, minus 1, which is minus 7. And then we find the adjoint, which is 2 minus 3 and minus 1 minus 1. So the inverse is going to be minus 2 upon 7, 1 upon 7, 1 upon 7, and 3 over 7. So A can be written as minus 3, 1, 1, 2 times 0, 7 times minus 2 upon 7, 1 upon 7, 1 upon 7, and 3 upon 7. So now you can do whatever you want with it. Like if you want to find the powers of A, you can do that by just squaring these. So you just need to find the squares of these, and that's just it, right? There are other important applications of diagonalization, such as solving difference equations, which is basically discrete approximations of differential equations. That's one application that I'm really interested in talking about. We'll talk about that in the next lecture. Today we're just going to do a couple of examples and look at it. One more thing that we should really talk about is when is diagonalization not possible, right? So let's go to an example where we couldn't diagonalize it, right? Did we do such a case in the last lecture? Eigenvectors. So we had two eigenvalues, two eigenvectors in this case. I don't think we did a case in which diagonalization was not possible. So let's do an example where diagonalization may not be possible, right? So we have, let's say, only one independent eigenvector. Let's see if we can find an example of that, right? So let me just check for an example. So let's try this one. let's say A is equals to 1, 1, minus 1, minus 1, right? This matrix is still singular, so there's still a chance that it might be diagonalizable, but let's find the eigenvalues first. So for the eigenvalues, we do determinant of A minus lambda I is equals to 0, which means 1 minus lambda, 1 minus lambda, minus 1, and 1. Sorry, minus 1 minus lambda, 1 minus lambda, and this determinant should be equal to 0. And then we multiply them, 1 minus lambda, minus 1 minus lambda, and plus 1 is equal to 0. So what do we have here? We have minus 1 minus lambda, plus lambda, and plus lambda squared, plus 1. So these cancel out and these cancel out, right? So we have only the 0. Have I done this correctly? Plus 1 minus 1, yeah. So I only have the 0 eigenvalue, right? This lambda is just equals to 0. So if I try to find the eigenvectors now, what do I get? I try to do 1, 1, minus 1, minus 1. And if I subtract the eigenvalues from it, so I have to do A minus lambda I have to find the null space of this matrix, which means times x is equals to 0. Since lambda is 0, A minus lambda is just going to be A, right? So I don't need to write this, but let's just write this as AX is equals to 0. So I need to do this, right? And if I put this as 0, 0, what do I get? I know that both the rows are the same, which means this is just going to reduce to 1 minus 1, 0, 0, 0, 0. So the first is telling me x1 minus x2 is equals to 0. X1 is just equals to x2. So I got one eigenvector, which was x is equals to x1, x2 is equals to just, these are both the same entries, right? I can say alpha, alpha. So alpha times 1, 1. Okay. So these are this is the eigenvector, right? So in this case, what I had was one eigenvector, which was eigenvalue, and one, so which was a repeated eigenvalue, and just one eigenvector, right? So we've seen different cases, and now I can classify them into different cases, right? So what happens is, if you've noticed that, let's say when you have, when we had two eigenvalues, we did get two eigenvectors. So once you have n eigenvalues, you will get n eigenvectors. But if you have only one eigenvalue, right, sometimes you may get, so for example, I think we had a repeated eigenvalue somewhere here. Yeah, we had one eigenvalue, but we still had two eigenvectors, right? And so even in this case, I believe there were multiple eigenvalues, right? So the idea is as follows. So if A is, so if A is n by n, and it has n distinct eigenvalues, then it will have n independent eigenvectors. But if it has less than n distinct eigenvalues, right? So there are distinct eigenvalues, which means another way of saying this is it has some lambdas are repeated. Lambdas are just eigenvalues, right? Are repeated. Then there are two possibilities. It may have n independent eigenvectors, or it may have less than n independent eigenvectors. So the idea is when is the matrix diagonalizable? In this case, it's definitely diagonalizable, right? Because we have n independent eigenvectors. Even in this case, it's diagonalizable in this case, but this diagonalization will break down if you don't have n independent vectors. And here is the place where I want to introduce two terms which really encapsulate this idea. So the first is the idea of algebraic algebraic multiplicity, which is um, which is the power of lambda. So for example, when you were solving the equation, right, when you were solving, if you get in your polynomial, let's say your characteristic, let me demonstrate the idea of algebraic multiplicity. So characteristic equation, if that looks like something like this, right? Let's say I solved a determinant a minus lambda I equation, and I got the following polynomial. I got lambda squared times lambda minus 1 cubed lambda minus 2 is equals to 0, right? So this was definitely perhaps a 6 by 6 matrix, right? Because we have 2 powers here, 3 powers here, and 1 power here. So let's say A is 6 by 6, right? And so the algebraic multiplicity, let's find the eigenvalues first. So the eigenvalues are lambda equals to 0, lambda equals to 1, and lambda equals to 2 by solving each of them independently. But this eigenvalue has an algebraic multiplicity of 2 because it was factorized twice in this characteristic equation. Similarly, this one has an algebraic multiplicity of 3, and this one just has an algebraic multiplicity of 1 because it just appeared once in my factorization of the characteristic equation. So that's algebraic multiplicity. The second idea, the notion, is of geometric multiplicity, and that's associated. So the geometric multiplicity of an eigenvalue is the number of independent eigenvectors associated with lambda, right? So for example, if I do am, so for let's say lambda equals to 0, I found that there are 2 independent eigenvectors. I was solving a minus lambda I x equals to 0, and I found 2 independent vectors. With lambda equals to 1, I found 3 independent eigenvectors. So I'm taking the nice case right now. And for lambda equals to 2, I found 1 eigenvector, right? And so in this case, what's happening is that the algebraic multiplicity of each of the eigenvalues is equals to its geometric multiplicity, right? Am is equals to Gm. Even in this case, we have algebraic multiplicity is equals to Gm. The problem arises when the algebraic multiplicity is greater, or the geometric multiplicity is lesser than the algebraic multiplicity. For example, if I had 2 independent eigenvectors, then in this case I would have geometric multiplicity less than the less than the algebraic multiplicity for lambda equals to 1. And as soon as you have any eigenvalue with this problem, then it immediately tells you that this is not diagonalizable. So another way that we can state the notion of diagonalizability is we can say that A is diagonalizable if for each lambda the algebraic multiplicity is equals to the geometric multiplicity, right? That the number of times it appears in the characteristic equation should be equal to the number of independent vectors that it has, right? Okay, that's it for today. I'm going to keep this lecture short because this just contains the basic ideas of diagonalization. We're going to talk about the applications of diagonalization in the next lecture, and I would like to stop here.